today we're going to look at travel graphs. Okay, so we're going to look at travel graphs. Travel graphs, they're in two. That you study, of course, they're in two. The first one, it's called a distance time graph. So the first one is called a distance time graph, and then the second one is called a speed time graph. Okay, so a distance time graph, it simply means it will be giving you the change in distance over time. Okay, so how is the distance changing? What's the distance for a particular instance? So you can think of it as just a graph, and this graph you're supposed to understand or interpret what will be happening in real life. Okay, so for example, Julia drove from her home in Derby to London. Okay, she went shopping and then and then drove back home. So you're actually supposed, especially if you're doing physics, you're actually supposed to be able to describe this curve here with some precision, at least in qualitatively. Okay, so here they are saying that she drove to London, so it must have been this leg here. So from this part here to this part here, it must have been when she was driving to London, and here the distance was changing over time. And then she went shopping, so the time that she'd be shopping would be this one. How do you know that? Just because we know this because her distance is not changing. Okay, so imagine you're driving a car and then you get somewhere. Um the meter for distance, the distance meter for the car, look up what that is. There's a special name for it, so look up what that is. But this meter would stop there. Okay, that's the meter where you read your mileage and all that. So it would be at a stop. Okay, so it would be at a stop just because you're not moving. So this happens when Debbie is doing a shopping, so the distance is not changing. But then afterwards, now she actually has to go back to her home, so the distance starts changing again. And this one, it's actually a displacement time graph, just because it's considering direction. Okay, if it were a distance time graph, it would have gone like this, and then up again. Just because we're not concerned about what direction she's moving, we're concerned about the path that she's taken and the length of that path. But then here, this one is called a displacement time graph. But for those who are studying mathematics, then there's very little difference. The concepts that I'm going to discuss with you today will be applicable still. So here you're asked to find the distance from Derby to London. So distance from Derby to London. So here from Derby here to London. Okay, so what distance is it? So the distance, remember, is the vertical axis. So it got from 0 to 70. Okay, so this one would actually be 70 kilometers here. Remember, this is the working that we do would be different for a distance time graph and a velocity time graph. For a distance time graph, the distance, it's actually just an ordinate. Why? Because we have distance already on our axis. Okay. The times she spent shopping in London, so the time she spent, so you're looking at this time interval here. From here, we say that that's when she was at a stop. So she was at a stop for this interval here. Okay, so you want to figure out the time there. So the time would be this one. Remember, this is 8 hours, and this one, it's 2.5. So it's 2.5 here. So if you want, you can actually write the coordinates for this. So this part here would be 2.5, 70. Okay, then this part here would be 8 hours and 70 again. Okay, so for you to get the time she spent in London, so the time she spent here, which would be the difference between the x-axis. Why? Because the x-axis is the time, the horizontal axis is the time axis. Okay, so it would actually be time. So you can say delta t, just simply means change in time, equal to then it's equal to 8 minus 2.5. Okay, so 8 minus 2.5, you get 5.5. Okay, don't forget to put your units. So it's actually 5.5 hours here. So it'd be 5.5 hours like this. That's the time that she spent. This one, it's actually very good etiquette. Okay, so whenever you have you know, any change in the shape of the graph, just label those parts according to their coordinates, so that you just use the values instead of having to look up again what's this. Okay, the average speed for her journey home. So a journey home would be from here to here. Okay, she's done a shopping on the spot. Now she has to go home. So a journey home would be from here to here. So average speed equal to total distance divided by total time. Okay, so total distance divided by total time, that's the average speed. So here our total distance is 70. Remember, a distance now, it's starting from 70 and then going back to 0. So the distance must be 70 kilometers. Okay, then the number of hours now, you see she's starting at 8 and she's ending at 10. If you want, you can even say 10 minus 8 here. Okay, it's still fine. Hours, and then you get 70 kilometers for every 2 hours. So here you'd get 35 kilometers per hour. Okay, so 35 kilometers per hour. So this is how you do it. So remember, you have to identify what part of the graph they're referencing. In our case, they're referencing for a journey home. So you have to know. That's why I was saying you should be able to explain qualitatively what part does what. So for example, this part, she was going to London from Derby, and then on this part she was doing a shopping, and then on the other leg now she's going back to her home. Okay, so this is why we got you know, this speed here. So that's pretty much it. Let's see if we can, and remember, distance time graphs and speed time graphs, they're quite different. Okay, so we're going to move over to the next question. So the next question says Hazel went on a cycle ride. So she has a bicycle and then she's just cycling. The travel graph shows Hazel's distance from her home on the cycle ride. Okay, so how far is Hazel cycled after 10 minutes? So this is time in minutes. Always take care to note the units here. Okay, so this is time in minutes. This is distance in hours. Previously, it was time in hours. Okay, so you actually have to know this part. Okay, so how far will she have traveled after 10 minutes? You have to identify where the 10 minutes is. So the 10 minutes point, it's this one here. Okay, so you have to identify here to say, okay, what's the distance, what's the change in the distance. So she's starting to from your home is the 0 point. We know this just because the gradation, it's in twos. Okay, so if this one is 2, 4, 6, so this one must be 0. Okay, because it's the same length here. So this one must be she have traveled 6 kilometers here. Okay, so we identify where is the 10 minutes, it's there, and then we extend and see where the 10-minute line meets the curve, and then we can read off of the curve the distance. Okay, the distance, remember, that's the vertical axis. How long she took a rest. Okay, so yeah, from here to here, that's when she was at rest. Remember, for distance time graph, a flat line means that somebody is at rest. It means that the distance is not changing, so they must be resting somehow. Okay, so to get this rest here, you have to, if you want, you can even mark. Okay, so this one will be 13, so this one will be 20, so it's 20, 13 like this, and this one will be 45, and that one will be 13. Okay, so Yeah, you want to know how long she took rest, so you can just subtract the x-axis. Why? Because we're starting from here to here, the time axis here. So that's what we need um to do. Okay, so delta t equal to 45 in minutes, okay, minus 20 in minutes. So this is actually equal to 25 minutes, and that's it. Okay, so you can write 25 minutes here. So the next part asks how far she cycled in total on a ride. This one you have to be careful with that. So depending if you can explain this graph, then it'd be easy for you to actually compute how far she cycled in total. For the previous question, it says the distance traveled in a return journey, but then right now they want for the total journey. Okay, so she will have traveled from here to this point here. It's 13 kilometers. Okay, so from here again back to this point, it's 13 kilometers again. So the distance equal to, so total distance, you can write this one, it's sigma. Sigma, anyone who is marking your paper, who would be marking your paper, they will know that sigma just simply means total. So here it's 13 minutes. So they're saying, okay, so it's 13 what? Kilometers isn't the distance, plus the distance for the return journey, which is 13 kilometers again. So thereby you get 26 kilometers here. Okay, then that's it. So this one must be 26 kilometers. Take note, we are doing distance time graph. If we're doing speed time graph, it changes. Okay, so this is it. Let's move over to the next part. So the travel graph below shows Cody's journey from his home to his school and back. So again, it's essentially the same thing. Let's see if they will ask anything differently. Okay, so yeah, so there's this part here. So this one will be a very good question. The distance to his school, that's what you have to find. So from here to here, again, we said for a distance time graph, we just have to look at the vertical axis. What's the change there? So it's starting from 0 to 12. Remember, it doesn't always start from 0. Sometimes it starts from somewhere else. Okay, it can start from 4 or anything like that. So what you want to do is to subtract. So distance to his school, you can say change in distance here. So this one is actually a triangle. It's not an A. So changing distance equal to, then you're thinking what's the distance ordinate. So the distance ordinate for this, it's actually 12 kilometers, okay, minus the first one here, it's 0 kilometers. So the distance to his school is simply 12 kilometers here. So let me double check something. So the speed for the first 20 minutes of his journey, okay, for the first 20 minutes, so this first 20 minutes is this. Okay, so the speed, when they're asking you for speed in a distance time graph, speed, it's equal to gradient, okay? So it's equal to the gradient. The speed equals the, hey, I wrote gradients, Jesus Christ. It's equal to the gradient. The gradient means the, remember, speed, when we want to measure the speed, when we want to write the units for the speed, it's usually maybe kilometers per hour or meters per second. This simply means that we are dividing the distance by the time. Okay, these are distance units, these are time units. Okay, whenever you have such a change, it's simply a change in okay, let me actually illustrate this. So kilometers per hour, like this, it's simply a change in distance, which is kilometers here, over a change in time. Okay, so a change in time like this. So if you see here, this one is what we define as the gradient for this curve here, because changing distance, it's actually the vertical, so you can think of it as delta y here. Okay, then change in time, you can think of it as delta x. So you're actually dealing with delta y over delta x. This is simply the gradient. This is how we define the gradient. Okay, so whenever you're asked to find the speed for a distance time graph, the speed is the gradient. So here, just remember, kilometers per hour simply means distance over time. So distance over time is actually the gradient for the distance time graph. Okay, so here you're asked to find the speed for the first 20 minutes. So what you do is you want the gradient. So here we're going to label this. So this one would be 20 minutes. If you want, you can go straight up directly by writing and by changing to hours. But then I advise you just keep it in minutes. It's still fine. So 20 minutes, and then this one, the vertical would be 12 okay, kilometers here. Okay, that's for this point. For this point here, you also have to do the same. So for this point, it will be 50 minutes. So it'll be 50 minutes. Then the vertical axis will be 12 again, kilometers. Okay. So what you want is for this one, which is 0, 0. Okay. So here, in order for you to get your change in x and change in y, what you do is you say speed, which is b part speed. Remember, we want the speed which we say that the speed is gradient for a distance time graph. If it's a velocity time graph, it's different. If it's a speed time graph, it's different. Okay, but then for a distance time graph, the speed is the gradient. So the speed equal to 12 kilometers. Okay, so changing y over changing x. Okay, so minus 0 over. So we started with this, going this, so we have to check this again, going that. Okay, so it's 20 minutes minus 0. So what I did here was I concentrated on this coordinate. I took change in y, so 12 minus 0. So on the change in x, I should also go back and take the x ordinate here and take the x ordinate here. So what you get here is you get 12 divided by 20, which is 0.6. Okay, so that's simply 6 over 10. So you get 0.6 kilometers per minute. Okay, so normally we write speed in kilometers per hour. So you want to change this per minute to per hour. Okay, so the way that you do it is you use what's called a conversion factor. Essentially, it's a one that you use to change from one unit to another. So here we want to convert from minutes to hours. So the conversion factor would be 60 minutes per hour. Okay. So here the way that I derive this conversion factor is I want to get rid of minutes. Yeah. So this is how I do it. The minutes, they have to be, since this one is on the denominator part, the minutes have to be on the numerator part. And then I want to be left with the hours. So my conversion factor is from minutes to hours. Okay, so this one would be my conversion factor. It helps you actually consider the units, just because you see how they cancel out. So for example, I can cancel out this way, and then here you actually get 36. Okay, so it'd be 36 kilometers per hour, just like that. Okay, so you get 36 kilometers per hour, like this. So remember, if you want, what you could have done is to actually change right on, to change this one into hours. Then you would have had 1/3 hour here. Okay, 1/3 hours. And what you do is you'd say speed equal to, then you would say distance over time. So the distance would be, so you would be saying distance here. I advise you to actually write divided by time, because here the problem is if you just say distance over time like this, your time is a fraction. Okay, so that's a problem. So what you do is the distance, the change in the distance, it's a 12, it's the change in the distance is 12 minus 0, so you actually get 12 kilometers here. Then divided by the time is 1/3 what? 1/3 hour. Okay, so if it's divided, then you can actually multiply by the inverse. Okay, So it would be 12 kilometers multiplied by, this one is simply h over 3. So you get 3 over h like this. Okay, so you get 36 kilometers per hour. But I don't advise you to use this, just because you actually have to highlight sometimes the concept of gradient. And if this is not starting at 0, it can become really messy. Okay, so yeah, so I advise you to just use this, and then you'll be fine. Let's quickly move over to the next question. Oh wait, there's another part here. It says the speed on his return home. Okay, so here I want you to actually attempt it and then see what you get as I rub this part here. You just pause the video and then attempt using the same method that we're using here and see what you get. So this point here, we need to define it because you want the gradient. We said speed is simply gradient. Okay, so this point here, it would be, this one is 65, this one should be 75. So 75 minutes and 0. Okay, so I didn't write minutes here just because you know, there's no space, but it's essentially 75 minutes and 0. So the speed would be the gradient. So you can actually say speed equal to gradient from G, this one to this one. So you can say from point A to point B or something like that. So you can write the interval, so 50 minutes to 75 minutes, it's still fine, whatever suits you, but then it's essentially the gradient here. So the gradient, it's equal to change in x, so change in x, change in y, so change in y is 12 here. So it's 12 kilometers, so 12 kilometers minus, this one would be 0 kilometers. Okay, so over, since they just want the speed here, it means that they just, you can get it as negative, but then you'd have to convert it to you have to check the positive for that negative. Okay, so we'll actually do it using the negative. Okay, so we start with 12 here and minus 0, so we're going to start with this one here. So it'd be 50 minutes minus and 75 minutes. Okay, so we'd actually get 12 kilometers divided by negative 25 minutes. Okay, so here we need to convert this again, just like what we did the last time. You convert this by 60 minutes per hour. This conversion factor is not only unique to, it's not unique to the stuff that we're working out. You can also use it in a variety of ways, maybe in density as well. You have suitable conversion factors for that. Okay, so what I want to do is to use a calculator. So using my calculator, I would get, so it's 12 divided by 25 multiplied by 60. Okay, so I actually get 28.8. So 28.8, negative here. So you can say, was here to say the magnitude of gradient. Okay, so this is the magnitude of gradient. This is the magnitude of gradient. So you get negative 28.8 kilometers per hour, because these ones they'll cancel. Okay, so now you'd have this, which is equal to 28.8 kilometers per hour. Okay, speed, it simply means we're concerned about the path or the rate of change of distance in the path. We're not concerned about whether it's negative or not. Okay, so if you're going to your shops, maybe your speedometer is reading 6 kilometers per hour, and then when you're coming back it's reading 6 kilometers per hour. That's your speed. Okay, so that's your speed. And then also same with distance, you've covered 5 kilometers going there, and then you're now covering 5 kilometers coming back. The magnitude is simply the distance. If you're doing physics, then you have to know the difference between distance and displacement. Displacement, we are just as much concerned about the size of the distance as the direction as well. Okay, so one direction would be positive, and then the opposite direction would be negative. let's quickly move to the next question. So next question is, it's kind of interesting a bit. Let's see if yeah, they'll actually have interesting parts as well. So the distance time graph below, it shows the journey of a businessman made from London to Liverpool via Leicester, and the direct journey back back to London. Okay, so I don't know how to pronounce this. I think it's Leicester. But anyway, the distance to Leicester, so the distance from here to here, some of these things now you're able to just write them. So this one, it's coming from the 0 point, so it's coming from the 0 point here, and then it's coming up to 65. So you just know 65 kilometers. Oh, so it's actually 70. You see the gradation here. This is 20, 40, 60. So it actually goes in between as 70 here. So 70 kilometers. Be careful of such things. So the time spent in Leicester. So spending time, we say that is the horizontal axis here. So it's coming from this one, from 2.5 to 4. So you'd actually say 4 hours minus 2.5 hours. So here you'd get 1.5 hours. Okay, so the time spent is simply 1.5 hours here. The speed you traveled from Leicester to Liverpool. So from Leicester to Liverpool, you want the speed. Remember, speed is gradient, exactly. Now you got your hang of it. Okay, so see, speed equal to gradient. But then remember that this is for the distance time graph. Okay, so gradient. So here we need to define our point. Here it's 4, then it's 75. Oh, we had said that it's 70. I keep saying 75. Jesus Christ. So and then this one it's 7, and it's 180. Okay, so the gradient is equal to 180. So 180 kilometers minus 70 kilometers. Okay, over then our change in time, it's simply equal to 7 hours minus 4 hours. Okay, so here we get this 110 kilometers here, then divided by this one will be 3 hours here, then we'd get 110 divided by 3. So I think we are going to adjust our answer to the 3 significant figures. So you'd actually get 36.666 and so forth. Okay, then you say this is equal to 36.7. Then you write 3SF. Okay, so to 3 significant figures, this is 36.7. So 36.7 kilometers per hour. Okay, so now you're asked to find the average speed for the whole journey. For the whole journey, it's equal to, we had done this already. So average speed it's equal to total distance. So you can say total distance traveled if you want, divided by total time. Okay, so you're just concerned about the total distance traveled. So here he's traveling up to 180. Don't worry about there's dynamics in this curve. Okay, these changes in the curve. Just remember where he starts and then where he ends up. It's 180, and then he has to go back again. So this one will be 360. You can say 180 kilometers plus 180 kilometers. Okay, which is 360. Then we're going to divide this by the total number of hours. So it's 0 up to, this one is 11, so this one must be 11.5. Okay, so this is 9.5, this is 10.5, this must be 11.5. 11.5 hours. Okay, so it's 360 divided by 11.5. So you'd actually get 31.3. Okay, so 31.3. Okay, kilometers per hour, 3SF. And the interesting thing that I want you to stick to your head, to your mind, is that when you're calculating average speed for the whole journey, you actually consider the stops as well. Okay, they're actually part of that journey. So we actually consider from going from 0 to 11.5 the hours, you including the time that this person here spends, at a stop. You actually have to include that. So that's an interesting observation. So now we're going to our speed time graph. So a speed time graph, we're going to do 1, 2, 3, 4, 5 questions. Okay, let's see. So the speed time graph, this now is different. We're dealing with the distance time graph. Now this is a speed time graph. It means that we're dealing with a different set of stresses. Okay, so we are interpreting the gradient differently, and then we're also introducing the idea of area under the curve. Okay, so area under the curve, you don't discuss it in distance time graph. You only discuss it in speed time graphs. Okay. So the speed time graph, it shows a non-stop service of the really short, the really slow, okay, of the really slow train traveling from Bangkok to Chiang Mai. Okay, so from Bangkok to Chiang Mai, and then you're asked to find the time to accelerate to a constant speed. So you see, you actually have to know what exactly they're talking about. Okay, so here the way that you'd interpret it is, if you're in a car and then you step on the gas, so you're accelerating your speedometer, you can read that, oh, it's increasing, it's increasing, it's increasing, it's increasing. That's what's happening here. We call this increase in speed, we call it acceleration. Okay, if it's a constant gradient, we call it constant acceleration. Okay, so you always be dealing with a constant acceleration. So this one would be acceleration up to this 90 kilometer per hour mark. Afterwards, the speed is not changing. That means that the person is traveling at a steady speed. So he's just maintaining. It's not moving faster. The speed is not increasing. It's not decreasing. They're just maintaining a certain speed. So this one, it's the constant speed phase. And then here, this one we call it deceleration. Okay, so the person is actually braking. Now they are starting. It's 90, but then it's decreasing to 0. Okay, so for a speed time graph, we did for a distance time graph, we needed to work with either points. So when we calculated the distance or the duration, we were using either points. We were just using points, so for the vertical axis and for the horizontal axis. In speed time graph, it's slightly different. So in speed time graph, one, it's different in that area under the curve is distance. Okay, so area under the curve is distance. So if you want to actually find the distance for the here for the 1.5 hours, you actually have to find the area here. Okay, the area under this curve for that interval. So that's the difference there. And the reason this is so is that you can think of it as if you would want to find distance, you have to say, let's say you're in primary school and then you want to find distance, you'd have to say speed by time. Okay, so when two entities are multiplying in this formula like this, in physics, these ones, it shows that it tells us that if you plot a graph of this against this, your distance should be area under the graph. Let me show you something in order for you to have a better idea of this. So let's say this is speed equal to distance over time. The distance is dividing by time here. So we say that you get the speed from the distance time graph as the gradient. Okay, whenever you have these quantities dividing, it's the gradient. Whenever you have two quantities multiplying, it's the area under that curve. If you're doing physics, or you want to advance doing physics, you learn a lot about these curves. Sometimes, for example, force by time. So force by time, it's actually let me give you this quick example. So force by time. This is called impulse. So this one it's impulse. Okay. So it means that for the force time graph, you get impulse from the area under the graph. Why? Because force and time they are multiplying. Okay, so whenever you have stuff multiplying, you actually get the quantity here from multiplication. So area under the curve, if this is too dense for you, just remember that for a speed time graph, area under the curve is distance. Okay, this is one of the tenets. And then gradient, it also has meaning. In the distance time graph, the gradient was the speed. Okay, so the gradient is, it's called acceleration. Okay, so acceleration is the rate of change of speed for our case, but it's actually rate of change of velocity. But rate of change of speed, it will suffice for maths. Okay, so for maths, you can say rate of change of speed. These two tenets here, these are what you should commit to your mind. So I advise you to just pause the video and then just recall what are the two tenets that you're supposed to remember for your speed time graph. And then these are the two. Okay, so you asked to find the time to accelerate to constant speed. Here they want you to identify the change in the graph. Okay, so from here to here, constant speed phase, it's this phase here. That's the constant speed phase, because now the speed is not changing. Okay, so the time taken to accelerate to the constant speed, it must be this interval here. So here from here. Okay, so A, you can say delta t here equal to, then this one is what? This one is 1.5 hours minus this one is 0 hours. So you just get 1.5 hours. That's the duration. Okay, so 1.5 hours. This. So the constant speed of the train. So now you want constant speed. Constant speed is simply this one here. So it has to be the 90 kilometer per hour mark. 90 kilometer per hour mark. Why am I writing 70? I'm saying 90 and I'm writing 70. So 90 kilometer per hour, this is the constant speed. It's non-changing. That's why we are saying that it's constant. Okay, the acceleration of the train at the start of the journey. So you want the acceleration. We had said one of our tenets, we had said the acceleration is the gradient. So in order for you to calculate the gradient, you actually have to use the coordinates here. So this one would be 0, 0, and this one would be we said 1.5. So 1.5, 90. Okay. So remember the units as well. We should keep in mind. So the acceleration, you should see. So the acceleration, you can just show them that it's equal to, you can just tell them that it's equal to the gradient. And then once you do that, now you say changing. So it's 70. Why am I writing 70? I like 70 so much. It's 90 kilometers minus 0 kilometers here. Oh, it's 90 kilometers per hour here minus 0 kilometers per hour divided by the change in time. So change in time, it's 1.5 hours minus 0 hours like this. Okay, so you'd actually get 90 kilometers per 1.5 hours squared. Okay, so yeah, so we were going to leave it in the units that we were given it, but essentially you can actually convert this. In fact, let me show you how you can do that. But then for now, you get 60. So you get 60 kilometers per square hours like this. Okay. So we had kilometers per hour here, and then we're also dividing by hour. So you have kilometers per hour, and then you're dividing by hour here. So this is equal to kilometers per hour. Divide, you multiply. Then when you multiply, you invert. So this one will be this. So that's why we get kilometers per hour squared like this. Okay, so our answer is actually 60 kilometers per hour squared. But you can change this to the usual unit for acceleration. It's actually meters per second squared. So you can change this. This is how you do it. So it's 60 kilometers per hour squared. So I always encourage you to write the units as this. When you're converting, write the units in fraction form. You want to change from kilometers to meters. So you can, the conversion factor would be 1000 meters here. So it'd be 1000 meters per kilometer. See what I did? 1000 meters and kilometer, they are simply the same. So this is essentially one. But then what this will help us do is to cancel the kilometers here. So 1000 kilometers is equal to 1000 meters is equal to 1 kilometer. So that's why I did this. And then you also have to change the hours to seconds here. So the conversion would be, so 1 hour here is equal to 3600, okay, seconds. So here you want to do it for hour squared. So this one should be squared, such that you're dealing with 60 kilometers per hour multiplied by 1000 meters per kilometer multiplied by h squared per 3600. 3600 is also being squared by s squared, like this. Okay, so you go to your calculator, and before you go to your calculator, you actually see that this cancel. Okay, and also this cancel. So you just have 60 multiplied by 1000 divided by 3600 squared here. Then you get 0.0046 meters per second. Okay, so this is how the person was decelerating. So here we used two conversion factors, which is quite interesting. If you can just follow this and then see. This one is how we convert, because the thing is we want hour squared. So we actually have to think, okay, what's the conversion factor from hours to seconds? Then we just have to square that. And when you square that, take care to change the units here. Another way to do it would actually be to change the 90 kilometers per hour to meters per second. Then afterwards, you also change the 1.5 hours to seconds as well. Then you'd get what we got here. Okay, so that's it. Let's quickly move over to the next part. Yeah, exactly. So this one is more like this is what you actually get in ZIMSEC, because they don't want to test your knowledge of conversion factors in the way that I was explaining it. So here are the distance, the speed time graph, which below it shows the journey of a train between stations. Okay, so it's going from one station and to another. And then you ask the time to accelerate to your constant speed. Again, this is the constant speed. So the time would be this. Okay, so the time would be this vector here. So you have to read the room, and let's say that this is 20 to 40. So here we have 1, 2, 3, 4 gradations. Okay, so we have only 4. So each one must be worth what? Each one must be worth 5. So it can be 25, 30, 35, 40. So each one must be worth 5 seconds. Okay, so this is actually 25 seconds. So there's this case, this thing of the time taken, the ordinate, reading off of the ordinate. You actually have to be careful, depending on the gradations. Usually there are 5 here. If it's there 5, that means that each unit is worth 0.2 per unit. Okay, per that unit of that length. But then for our case, we had only 4, so these ones, they make sense. If you would say each one is 5, so this one 5, this one would be 10, so this one would be 30, and then 35, and then 40. And then we were starting from 0 here. That's why I had to say directly it's 25 seconds, because it's 25 minus 0. So you ask the constant speed of the train. So the constant speed here is 70 kilometers per hour. Kilometers per hour. Meters per second here, that's the unit that we're using. Okay, so the acceleration of the train at the start of the journey. So you want the acceleration. The acceleration, we say that it's gradient. Okay, at the start of the journey, they mean for this leg here. So this one would be the 25 seconds that you identified, and 70 kilometers per 70 meters per second. Jesus, we're doing so much stuff on kilometers per hour that I'm just thinking of kilometers per hour right now. So this one would be 0, 0 like this. So acceleration, remember the acceleration for the speed time graph, it's equal to change in speed. So you can actually say gradient here, simply gradient, so that you save time. They will know that you identified it as the gradient. So you have 70 meters per second minus 0 over 25 meters per second minus 25 seconds minus 0. Okay, so here you'd get 70 minus 25 here. Write your seconds legibly. So this one should be a bit smaller so that we know that it's second. Okay, so this one would be 45 meters per second squared. Okay, so this one would be 45 meters per second squared like this. We're going to move over to our final question. So our distance speed time graph, it shows the journey of a train between two stations. Isn't it the same? Oh, so it's different. So the acceleration of the journey at the start. So the acceleration of the journey, we had say that this is gradient. So here is 0, 0. Always note the starting point here. Okay. Sometimes it's not 0, 0. Sometimes it's something else. So your calculation should reflect that. And then this one is they're still using the same scale, so it's 25, 30, 35. So this is 35 seconds and 80 meters per second. This time I got the units right. Okay, so A, acceleration equal to gradient, which is equal to, so you would say change in y, or y-axis is the speed axis. Okay, so 80 meters per second minus 0 over 35 seconds minus 0, then we get 80 divided by 35, then we get, they want us to round off to one decimal place, so it would be 2.3 meters per second squared to 1 dp. Okay, that's it. So this one would be 2.3 meters per second squared like this. Okay, so the acceleration is meters per second squared in the sense that, remember how the units are working out. Here you have meters per second, and then you also divide them by second here. So it means that meters per second multiplied by, you invert here, it'd be 1 over second. Then this one would be meters per second by second, you get second squared, which can be read as meters per second squared like this. So that's why the units are like that. Okay, so yeah, that's it. So B asks us to find the deceleration for the whole journey. So deceleration would be this part here. Deceleration simply means negative acceleration. The speed is decreasing. Okay, that's the deceleration. So the magnitude of that, that's what you're looking for. Okay, so this one, this point here, it'd be here. This is 120. No, just wait, 100. Then this is, let me actually extend line here. Okay, so this is 100. This is 5. 110, 15. Okay, so this one would be 115 second. Then we have 80 meters per second like this. So this one would be your ordinate, and this one would be 120. Where is 120? 120 is here. 125, 130. So 130 seconds and 0. Okay, so that's it. And so change in deceleration is equal to magnitude of gradient. Okay, the reason we are saying magnitude is we'll actually get a negative value there. So gradient, you can even say for the points here. So the points don't need to be only this and this, they can be even intermediate points, but almost always these extreme points there, they are the ones that are easiest to compute. So here you'd get 115 second, then 80 meters per second here, and this one is 130 second and 0 meters per second, like this. Okay, so your deceleration will be equal to change in y, so change in y, that's our vertical axis, so it's 80 meters per second minus 0 here, divided by, and we're also saying magnitude. Okay, so just remember that, or modulus, so here would be 115 second minus 130 second. Okay, so we're taking the magnitude here, so the magnitude would be 80 meters per second divided by, here we get 15 seconds. Okay, so it's equal to, so one would actually get negative 15. It's still fine, you can carry on with the negative, so 80 divided by 15, you get 5.3. Okay, so now magnitude simply means take the positive, so it would be 5.3 meters per second squared. Okay, so the deceleration is the gradient here for the negative acceleration here, or for the for the part where the speed is decreasing. Okay, acceleration is rate of change of rate of decrease of speed. Okay, the total distance traveled by the train in kilometers. So total distance equal to area. Okay, so total distance will be area for the whole curve. So you can say whole. Okay, so for the whole cave. So here we are dealing with, we want this area here. So the first thing that you need to do is to identify what shape you're dealing with. So this is actually a trapezium. Okay, this spot and this spot, they are parallel. So sometimes you can break down the shape into segments. Okay, so that you'll be able to calculate the total area. But then for this one, don't worry. Okay, this is simply a trapezium. So just recall that the formula for area of a trapezium, it's half a, it's half a plus b, right? So where a and b are the parallel lines times height. Okay, so why? Because it's the height here would be the vertical distance between those two parallel lines. So why? Because it's simply half AH plus half BH here, just because it's two triangles. Okay, so this is where we get the formula for the area of a trapezium. So some people write it as h over 2 times a plus b, still fine. So anyway, let's identify stuff. So our a, which is our axis here, it's equal to from here to, we had said 130. So it'd be 130 seconds here, plus this one here would be from 175. So this is 171. Is it 115? Okay, this is 115 minus. So if you want, you can even put big brackets here, so that you can write this one as, it's 115 minus 35, like this. Okay, so this one is your A, this one is your B. Now your h, which is the vertical height, it's equal to 80 meters per second. Okay, so from 0 to 80, just like that. So it's half. Then here you get 130 plus 115 minus 35. So you get 210 seconds multiplied by 80 meters per second. Okay, so what do you get? 0.5, which is half, multiplied by 210 multiplied by 80 is equal to 8,400 meters. Okay, so you need to change this. So it's 8,400 meters. Remember our conversion factor. Okay, so conversion, we're actually going to do a video on just conversion. Okay, conversion of units from one unit to another, just like that. We're going to do a video on that maybe next. So here we want to change meters to kilometers because we are asked to leave the answer in kilometers. So it would be kilometer. This time you want to get rid of meter, so you have to say kilometer at the top divided by 1,000 meters at the bottom. Okay, so it's simply a case of 8,400 divided by 1,000, which you get 8.4 what kilometers. Okay, so this is it. You're asked to round off to one decimal place, so you know it actually fits. So that's it. I'll catch you in the next video. Make sure you like, share, and subscribe. Yuba out.